I'll be there in a minute. Okay, very good. So now also officially for the recording, good morning and welcome back to our second day. Our first speaker is Lucas Timotheo Sanches. Do you want to share your slides? And as I said, for those of you online, I will log in a second and then monitor the chat and raised arms if you have any questions. You want to, oh yeah, get rid of any of it. If you click here on the three dots,
Okay.
then hide video pin.
Panel.
Yeah.
All right.
And then typically this should also have a height. Oh, doesn't have a height of this. So maybe you can,
Well, I can
just move it
this.
inside. Yeah. Okay. Very good. And then you can fix this to your shirt and put this in your.
Oh, right. Sure. Sorry, what? Participants to the other screen also. So I think this is in this computer. Yeah, so I can do like this, maybe. Yeah. All right. Okay. Good morning, everyone. Thanks for coming to my talk this early in the morning. And today I'm going to talk to you guys about some of the efforts we're having at LSU to speed up our binary black hole simulations. Mainly, I'm going to be talking to you guys about multi-step time integrators and our ongoing effort for a multi-patch system in CarpetX, right? So I am Lucas. I am a postdoc at CCT at LSU. You probably know me by now. So let's start, right? So CarpetX, everybody kind of knows what CarpetX is. CarpetX is the new driver for the Einstein Toolkit, right? It's the newest GPU-enabled adaptive mesh refinement driver. It's based on MREX, which is a software infrastructure for exascale structured block adaptive mesh refinement. And we are focusing on GPUs with CarpetX. And the reasons for that is twofold. Mainly, with the AI hype, GPUs became, the new hardware that all clusters are targeting, right? Because AI really likes to do things with GPUs. If we want to keep up with, the largest clusters that are being built currently, we have to keep up with that GPU trend, right? And GPUs provide us with high throughput, but they present, some extra challenges and some latency bottlenecks, right? And CarpetX has already been used for some production codes, GRMHD codes, namely AsterX. I think Jay is going to be talking about this later today. And GramX, these are both production GRMHD codes in CarpetX. And we are always looking for, doing our numerical evolutions faster, right? So using new hardware is one of the ways that we can do that. And using tricky hardware optimizations is one of the ways we can do that. But that's not the only way. We can also try to improve our numerical algorithms and try to do less work with our numerical algorithms, right? So one example of such improvement would be subcycling in time. That's when you have multiple adaptive mesh refinement levels and you allow your time step to vary across your refinement levels, right? And I think Leeway is going to be talking about subcycling in time today even. So today we're going to be talking about yet another way of improving the speed for binary black hole simulations by changing our time integrators, right? Reducing the algorithmic complexity in our time integrator mechanisms. So this is the point where I reveal to you that the title of my talk is actually a lie. I'm going to be talking about ODE stability theory because I think this is important both for students and for us to understand the things that we're trying to do with our methods, right? So here, as a motivating example, I chose something a little bit less complicated than the Einstein field equations. This is going to be based on a tutorial by Peter Diener and Guzman. They gave that on Trieste a few years ago. So this is going to be a case study of the 1+1 wave equation on a space-time that has, a non-trivial shift just to make things slightly more interesting, right? So we're starting with this two-dimensional metric, and we're writing the wave equation in this curved background. We can split the resulting partial differential equation into a system of coupled first order in time 3 differential equations, right? And in yesterday's tutorial, Steve was talking about the mole thorn, right? That's the method of lines thorn. So the idea behind the method of lines is we have a differential equation which has partial derivatives both in time and in space. And so we are going to use some approximation to turn our spatial derivatives into something, usually in the Einstein Toolkit, that's finite differences, right? So this semi-discretization turns this coupled system of PDEs into a coupled system of ODEs, right? And now we have total derivatives in time of our evolved quantities, and D here is going to be our discretized operator, right? So essentially, at some point, when you're solving the Einstein field equations, things are going to boil down to solving a system of coupled ODEs, right? And so let's consider, for instance, a generic ODE here, right? You have some generic state Y, you have some generic right-hand side, you introduce some initial condition and a discretization of that, right? This is just me defining notation. And there are basically two broad categories of ways to solve a generic ODE problem, right? Numerically. We have what are called the linear multi-step methods. Example of those are the Adams-Bashforth methods and the backward differentiation formula methods, right? And we got the good old Runge-Kutta family of methods, right? So basically what differentiates these two methods is the following. So here we are updating our state one step forward in time, right? And on a linear multi-step method, we are doing that by introducing a combination of the right-hand side evaluated at different points in time. So here I am taking the right-hand side at the current time step, and I am taking the right-hand side at the previous time step. So basically, we are combining past and current information to predict the future. The logic shifts on Runge-Kutta-like methods, right? Runge-Kutta methods introduce a number of stages. So this is RK4. So here we have 4 stages, K1 through K4, right? And what we're doing is we're evaluating the right-hand side not on the past, but we are evaluating it in intermediate points between the time step where you are and the time step where we want to get to, right? And then we perform a linear combination of those intermediate time steps to get the future time step. So in numerical relativity and in the Einstein Toolkit, as far as I know, all production runs use RK4. So this is a very, very widely used and popular method of evolving your equations in time, right? So the idea that we want to introduce here today is fusion, right? So we are going to combine both the ideas from linear multi-step methods and Runge-Kutta-like methods, right? So we're going to replace 1 or 2 of our stages of the Runge-Kutta time integrators by evaluations of the right-hand side at previous time points. So here we are computing the right-hand side at the previous step, and here we have the right-hand side at double previous step and previous step. Now, why does this prove an advantage? Well, since this information is coming from the past, in principle, and this is also being computed at K1, in principle, we can just compute the right-hand side, save that, and on the next step, we can reuse this information that was previously computed, right? So essentially, we get a 4th order method with 3 stages and 1 past time level reuse. And of course, we can also have a variation of that of reusing 2 previous time steps and only computing 2 stages, right? And that should speed us up because the most expensive part of any evolution is computing the right-hand side, right? So computing the right-hand side at intermediate time points is going to be the bulk of your work, especially in the Einstein field equations where that right-hand side is significantly very complicated. So you notice that these methods, they are, as presented here, they're really generic, right? And so our mission is to find these coefficients such that we produce a 4th order method and such that 4th order method that we find is stable and allows for a large time step to be taken in our evolutions, right? And that's why we need to understand absolute stability theory, because we use that in order to derive some of the coefficients of our methods in order to take the largest time steps that we can, right? So the concept of absolute stability was introduced in the study of linear multi-step methods, but that has been generalized, right? So the idea is that we apply our ODE solver to a model problem, right? Being the right-hand side is going to be some eigenvalue lambda multiplied by the state, right? And this, of course, has a known analytic solution, right? The solution is going to be of this kind, an exponential of lambda t. And the idea is that if we allow lambda to be complex, we say that the method is absolutely stable for all values of lambda times the time step in which the approximate solution at some time step n is bounded from above as n increases, right? So basically what you're saying is you don't want your numerical method to produce a solution that grows unbound, right? And the region in which this is satisfied is known as the region of absolute stability of a numerical integrator, right? So how do we find this region of absolute stability? Well, there's some math that's behind this. I don't want to really get into too much detail about this, but it involves finding a characteristic polynomial associated with the method, and then you find the roots of that polynomial, and there are some conditions on the roots, and then you get something that looks like this, right? So here we have the real part and the imaginary part of lambda h, right? And if lambda h falls within these regions here, we say that our method is absolutely stable. So here we have the absolute stability region for several different time integrators. So AB2 here refers to the Adams-Bashforth linear multi-step method of order 2. Here we have the good old Euler method. Here we have BU4, which is a method that was created by Butcher, which is of the same family of the ones that we are studying, right? So it's a hybrid method as well. And we got standard RK4 here. Now, if you remember Steve's talk yesterday, he was talking about the difficulties of the wave equation, and he mentioned that you couldn't do the wave equation without using the method of Leinsthorn because you needed a different kind of time integrator to do that, right? So when we did the heat equation example, we were using essentially the Euler method, right? We were just using the current time step to basically update it forward in time. Now, the wave equation doesn't really work with neither the AB2 method or the Euler method. You need at least RK3, if I'm not mistaken, to have any hopes of that working. And why does that happen? Well, that comes from the von Neumann stability analysis of your PD, right? So if we rewrite our wave equation in a more compact form like this, right, where we get the characteristic matrix of our system more explicitly written out, right, we can do a Fourier analysis of the error amplification factors, and this gets us to a Fourier transformed eigenvalue characteristic matrix with the eigenvalues of that matrix being now related to the absolute stability region, right? So in this case, we have purely imaginary eigenvalues for the Fourier transformed characteristic matrix, and the system will be stable thus if the product of these eigenvalues and the time step that we're taking is inside the absolute stability region. And remember, because we have for the wave equation some purely imaginary eigenvalues, right, the Euler method would outright fail to evolve it because it does not contain any section, or at least no part of the imaginary axis, right? It just touches the imaginary axis here at the origin. Whereas RK4 actually contains a part of the imaginary axis of the absolute stability region, right? And so we are searching then for a method, right, that contains the largest possible intercept value or the largest possible section of the imaginary axis for our methods. And this is what we're going to use in order to tune some of the coefficients of our hybrid time integrators. Yes? It would be. Oh, yes, sorry. So the question was, what would happen if I evolve the wave equation using the Euler method? You would get an instability, right? It's you don't have any hope of succeeding in that endeavor at all. Right? So this is really important for us to note in numerical relativity. Of course, we're evolving Einstein's field equations, but strongly hyperbolic systems share some characteristics, right? So this is why the wave equation is a good case study for that. Right, so here we are presenting the final result of all coefficients for our methods. So for the two-step methods, the ones that use one past information to compute the future, we have a family of two possible solutions that we studied and explored. And for the three-step method, the one that uses two previous time levels, we have a single solution family, right? And how do you get these coefficients? Well, firstly, you have to, basically do a Taylor expansion of a function, and you expand that to fourth order, and then you match it against, the prototype for your method, and then you get what are called the order equations, some equations that these coefficients of your method need to satisfy. But these equations, they're usually going to have some free parameters. In this case here, we have C2 and C3, the free parameters of our methods. And we tuned the free parameters of our methods in order to try and maximize this intercept value, or the value in which the absolute stability region crosses the imaginary axis. And this was done in hopes that this would give us the highest CFL, or the highest time step possible for our problems, right? And so now let's go through some numerical results and tests, right? So the first thing that we did is we did what's called a robust stability test for the BSSN-OK system, right? So that involves having the BSSN-OK system with Minkowski metric, and then you add some noise to it, and then you choose a time step, you evolve that for some time, and you see what happens when you increase the resolution. Now, the idea is that a conversion code or a stable code will not blow up when you do this, right? So here on the left, we have an example of what it looks like when things are not good, right? So you can see here that as we increase the resolution, the rate of increase of the Hamiltonian constraint with these noise evolutions just blows up and grows unbound. Whereas a passing robust stability test is going to look something more like this, right? You have another decreasing or a constant value for your evolution quantities, right? So this was test number one. We were looking for the highest CFL, the highest time step possible that we could get for a method in this test. The test number two is we used our methods to do binary black hole collision simulations, right? And here we are comparing our results against RK4. So these two guys are the two-step methods, one previous time level reuse, and then this is the three-step method, two previous time level reuse. Oh, I should mention that all of these evolutions were done with the CanudaX code, right? This is a CarpetX port of Canuda, which is a BSSN code. So we were happy that we saw, a good agreement with the evolution of the Hamiltonian constraint when comparing it against RK4. Our three-step method is the one that performs the worst here, right? So this is also a plot of the difference of the extracted waveform for psi420, right, on these evolutions. This is what an extracted multipole of the psi4 bioscalar looks like. It's visually indistinct from what you would get with RK4, right? But I just wanted to put it out there so that you guys can see that it actually works. And finally, we wanted to try our methods for some hydro evolutions, right? So we did basically two trials. We did the Balsara 3 test. We picked this test because this is the hardest of the Balsara test suite, right? Because of the very wide differences in ranges and scales. This is one of the hardest tests for the Balsara test suite, right? And again, we are comparing our methods against RK4, right? And surprisingly, our three-step method seems to do a little better here in this case. Yes? Oh, right. So the Balsara test is a standardized. So repeating the question was, what are the Balsara tests? So the Balsara tests are a standardized test suite of finite volume codes, right? The idea is you're going to initialize your your fluid quantities. Here we are looking at the fluid density, right, with some analytically known initial data solutions. And these, as you can see here in black, they have lots of discontinuities and bumps and weird things like that, right? And we do that because finite volume methods are supposed to be able to capture these discontinuities and bumps and whatnot, right? That's the whole point of using finite volume methods. And we want that in hydro because hydrodynamical quantities, when you're doing neutron stars, for instance, they present these discontinuities and difficulties, right? Okay, so moving on, we also tried our methods with a Kelvin-Helmholtz instability, and this is the obligatory cool video of the talk, right? This is the evolution of the Kelvin-Helmholtz instability, which looks nice. Here we can see the adaptive mesh refinement happening around the swirls of our Kelvin-Helmholtz instability using our hybrid methods, right? And so now we go to the summary of our results and the the good things and the not so good things that we found with this, right? So this table here summarizes the largest CFLs we could take for each of these different tests that I presented. So here we see CFLs we took for the Kelvin-Helmholtz instability, the CFLs for the Balsara-3 test, the robust stability test, and the binary black hole merger test, right? So we found that our two-step methods, the ones that use a previous time level, were really good. For binary black holes, our method performed really well. We have a maximum effective CFL, higher maximum effective CFL than RK4. What that means is effective CFL is basically the ratio between the maximum CFL you can use with a method divided by the number of stages that method has, right? We also found that they have good numerical agreement with the solutions we found with RK4. And we've measured a 30% speed up when using multi-step methods, right? We're still 3% off the theoretical maximum, right? Because you're eliminating one stage, so theoretically you can speed things up by 33%. Sorry. We believe that this 3% that we're still off target is probably due to some, I'm just going to get water. This is probably due to some linear combinations in the way that CarpetX does its right-hand side and ODE solving loop, right? Why is this not changing? Here we go, right? So our two-step methods, they did well on robust stability test and binary black hole, but things changed a little when we studied hydrodynamics, right? So for Balsara-3, the method just failed outright. And we're still kind of trying to understand why that happened. We have some hypotheses. We think that maybe in this case, what you want is not really such a tall absolute stability region, but you also have to have some width to your absolute stability region to allow you to include some of the eigenvalues that are in the real region, right? And we conjecture this because our three-step method works better in this case, right? And so the RK42 family, the two-step method family, did not produce any speed up for our hydro tests. In fact, they slowed the code down when we tried it because we had to reduce the time step. But if we were to use these methods for like a production neutron star black hole run with a limited CFL, they would still provide a speed up, right? So if we pick CFL to 0.35, they would provide a 4% speed up compared to RK4 still. The RK43 method, the three-step method, the one that uses two previous time levels, performed the best so it did worse in the robust stability test, but it was the best for our hydro evolutions, right? So if you actually compare the results from the robust stability test with the binary black hole collision test, it did a little bit better on the actual thing than in the robust stability test. And I believe that this is, of course, because on the actual binary black hole run, we have dissipation, whereas in the robust stability test, we purposefully disabled it so that it wouldn't cloud or or results. It did very well in the Mulsar 3 test, in fact, and has an effective CFL that's 70% larger than that of RK4, right, which was kind of surprising to us. But in the KHI run, the Kelvin-Helmholtz instability run, we just got a 2% advantage. But again, if we imagine an RK4-3 simulation with limited CFL, it should give us a 26% speed up relative to standard RK4, right? And like I said, these results they were unlikely for us at first because this method didn't do well as well as the others in the robust stability test and binary black hole runs. And some things that we like to do with these methods, right? We would like to try to understand better why things are not as good as we'd like in hydrodynamic applications. We have computed what's called the dense output coefficients for these methods that's required for them to be able to work with subcycling in time. And we are considering some variations of this idea, right? Using different kinds of past time level data. So instead of just saving the right-hand side, maybe you can save a linear combination of the right-hand side, and that gives you some stability advantages, right? Something that has been suggested to us and basically like a feature request was to see if we can get variable time stepping to work with this, right? Adaptive time stepping, which is what's called Runge-Kutta pairs. Basically, you have a fourth order and a fifth order Runge-Kutta method that can be computed kind of simultaneously, and you use the fifth order solution to predict your error and then adaptively change your time step. That also may solve some of our stability issues, because we noticed that, for instance, if you bootstrap the fluid evolutions, if you do more Runge-Kutta steps than RK4 steps than necessary, and then you switch back to the hybrid methods, they tend to perform better in these cases, right? So maybe adaptive time stepping can even solve that. And like I said, investigate the performance on hydro runs, make them run faster, and try to understand if maybe we want to change the shapes of our absolute stability region. Maybe we want it to be wide, not only tall, and so on and so forth, right? So now I'm going to switch gears and change the subject completely. And I'm going to talk about the latest developments in our multi-patch system. Yeah? Oh, there was a question. Yes, sure.
Well, I was just going to suggest that before you switch gears, it might be good to get questions.
Yes, that is. So are there any questions? So there's a question in the audience. Yes.
Instead of doing RK4, RK2, just do RK3 for everything.
So let me see if I understand the question. Why we didn't do RK3 instead of RK4? Is that what you're asking?
Yes, because for BSSN, you just need to go either in the partially implicit Runge-Kutta second order, or you just go to third order, and it also works, right?
Right. So the
you could do third order.
Right.
I don't know what the cost ratio is.
Right. So the question was, why did we opt for fourth order methods instead of second and third order methods and variations of RK2 and RK3? Basically, to our knowledge, RK4 is kind of like the standard that people use for binary black hole runs, right? So that's what we decided to modify at first. But in principle, there is nothing really stopping you from doing the same thing with RK3 and whatnot.
Want to make one?
Yes, sure. Go
Sorry.
ahead.
So I took the gallery example from the Einstein Toolkit, and I tried running it with RK3 to see what I could do. And it turned out that it was only stable if I took a time step that was 3/4 the size. So it offered no benefit. It got exactly the same speed.
All right.
Yeah.
A question.
Just unmute yourself and sorry, we come here. Octavio, can you just unmute yourself and ask your question, please?
Yeah, can you hear me? Can you hear me? Yeah?
Yes.
Okay, cool. Okay, probably the question is a bit similar to the one was just asked, but I was wondering, when we saw your table of the tests, and we could see that RK4, the standard one, is close enough to the other methods that you tested. So my question is, do you have in mind any like example or situation in which these new methods developed like can help to get better results or like yeah, I'm just looking for an example where to apply these new methods and compare it to RK4.
So if I understand the question is if we have an example where we get like an absolute advantage of the new methods.
Yes.
Right. So our best results are for the binary black hole runs. We've measured a 30% speed up of doing a binary black hole collision with our K42 1 and 2 family of methods, right? So this is the method that uses one previous time level. We measured a 30% speed up with this one with no apparent punishments on the CFL side. And we also, I'm just going to go back to this plot here. We also seem to have, good agreements with both the evolution of the Hamiltonian constraint and with the extracted gravitational wave that we got from these evolutions with these methods, right? So particularly RK42 parentheses 1, that's one of the methods. Right, this one seems to perform the best in both in terms of agreement and of speed. So for this problem, I think we can say that we have a clear win with these methods.
Okay, thank you. Thank you very much.
I guess I would also say that I would also call out the 26% that works from all the hydro tests.
Right, right.
That seems like the more significant thing to me.
Really?
I mean, you got a 26% that works the black hole and the hydro.
Sure.
And so that seems like
yes. Steve points out the 26% we also can get with some hydro run, right?
Any other questions here in the room or online? I'm not seeing anything.
All right. All right, so for the second part of the talk, I'm going to try to summarize some of the developments we're having with our multi-patch system for CarpetX. So these slides, you've probably seen them if you've seen any of my presentations last year, but of the previous years. But basically, a multi-patch system is this idea that we're going to decompose our domain of evolution into different coordinate patches, right? And this is very natural to do in general relativity because we describe our object of study or space-time manifold as something that can be covered in multiple coordinate maps and coordinate patches, right? And this is basically the idea. We're taking a piece of the manifold we're studying. We are covering that manifold with different coordinate system than just simply a global Cartesian system, right? And why do we do this? Well, we do this because using Cartesian coordinates is not always the best option in terms of memory efficiency and in terms of speed, right? So I have this very back at the envelope calculation here, right? So assuming you have 8 bytes per double precision floating point number, right? Let's think about what happens if you have a cubical domain and you have a fixed grid spacing in all 3 directions, and what happens if you have just this one variable, right? And if you have a step size of 0.1 and you want to increase your domain size, right? So increasing your domain size sometimes is necessary because you want to extract your gravitational waves far away, right? So we go from a, if the domain extends from -100 to 100, what you get is you get 8 gigabytes of memory that are required for this, right? But if you start doubling down on your grid extents, you start to get exponential increases in the memory requirement, right? And that also happens for resolution requirement, right? So suppose that now your grid has a fixed size, but you're increasing your resolution, which is something that, which is also something that we want to do for various reasons, right? You also get some exponential growths in memory. And that basically happens because on a Cartesian system, all grid coordinates are coupled, right? You can't just increase the resolution in one dimension. Well, I mean, you can't do that, but that would make your grid non-uniformly resolved. And this is not something you really want to do, right? And this is usually important because if we have a gravitational wave simulation, right, And let's say that we have, the interesting stuff happening here at the origin, or binary is evolving and is colliding and is producing a wave throughout time, right? And then we put our detector mockup at some distance away from the origin, right? And we want to measure the signal. That's also going to take some time, right, for that to happen. Well, at the same time, numerical computations, they need to have an artificial outer boundary. And there is no such thing as a perfectly transmitting boundary. All outer boundaries, they're always going to have some sort of, numerical noise and some reflections that come back from them, right? And so what we want to do is we want to place our outer boundary far enough so that the incoming data from the boundary doesn't interfere with the gravitational wave measurements that we are doing here. So this is why we want far away outer boundaries, right? And for that kind of thing, the smartest thing to do would be to use a spherical or spherical-like coordinate system, right? And this is basically because in this, you can decouple your radial and angular resolution. So usually what we want is we want a lot of radial resolution, but not so much angular resolution, right? Of course, the spherical coordinate system has a problem. It has a discontinuity, has a divergence at the origin, right? It is discontinuous at the poles, I'm sorry, right? So one way that we can remedy that is to basically split that up into, instead of using a single coordinate chart to cover the whole sphere, we use 6 coordinate charts to cover the whole sphere, right? And this idea has been used multiple times, has been used in Llama. It's used in apparent horizon finders. So basically, the coordinate system that we are working with our multi-patch system for now is a 7-patch system in which you have a central Cartesian domain, right? And that central Cartesian domain just joins continuously with your 7 spherical-like patch systems, right? And so CapyrX is the code that is implementing that in the CarpetX era, right? We're still developing and testing it, but we have some stated goals, right? We want it to be more easily extensible than Llama was. If you want we want people to be able to, create and experiment with new coordinate systems that do more interesting stuff, right? And for that, of course, you're going to need some rich documentation so that people can actually introduce new coordinates in the code. We want it to be as frictionless as possible for it to be integrated into existing codes. And this is something that we haven't started working at, but we want to support some customized boundary treatments, interpatch boundary treatments, meaning the ways that you're going to communicate information in between your coordinate patches. And we want some rigorous unit testing of the patch systems that we already have, thankfully, right? So what's the current status? Well, recently we got our first binary black hole and spiral collisions to work with CapyrX, but there's still a lot that need to be done, right? So in order to have this really, really working for production simulations, we have to fix some things. So the first one is our output files. Now, the output files for CarpetX, none of them support multi-patch grids out of the box. We already kind of have to hack a way around them, right? So right now, we support the silo and the OpenPMD format. The silo format is the easiest to use because you can just open visit the visualization program, just put them in there, and it should show you the grid and just works, right? But the problem is these files are big, heavy, and cumbersome, right? So whenever you try to do something that's more complicated than a wave toy, things start to get difficult, especially on the visualization side, right? It takes a long time for you to read the file and to plot the file. So this is something we want to optimize. This is a difficulty that I have encountered. So we can have box-in-box mesh refinement working with our multi-patch system, but for now it's kind of hard to set the boxes in their correct positions because you have to think in terms of local coordinates, and I don't really think that that's good for users. One difficulty we're facing is with gravitational wave extraction. So we have some simulations where we can get Psi4 evolving, but when we do a multipole extraction of Psi4, we get some nonsensical signals, and I still need to investigate why that's happening, right? And the next thing we want working, of course, is puncture tracking and horizon finding. puncture tracking works for a while, and then it no longer works because it's probably not ready yet to, understand multi-patch coordinates. But these are the items that are still needed for us to actually have, a real production binary black hole run. And so now I'd like to break out slightly and to show you some code on CapyrX, right? So I'm going to go here to the Jupyter notebooks, and everybody should have this, I think. All right, yeah, let me escape out of this. So, all right, so I would like to show you some things on the CapyrX WaveToy IPyNB notebook. You're free to follow along. Right, and so what I like to show you guys basically with this notebook is what kind of changes we have to make to our codes in order to make it multi-patch compatible, right? And this is me trying to, see if I if I got some sensible API out of all of this, right? So basically, what we have to do when writing multi-patch code with CapyrX is that CapyrX uses a global coordinate system that contains your spherical like patches, right? But when you're doing finite difference derivatives, you are implicitly, you are implicitly doing them in local coordinates. So you have to do these coordinate projections from local coordinate systems to global coordinate systems, right? And to do that, right, there were basically a few choices. I think Llama provides a thorn that's called global derivatives, and it takes care of that for you. Now, I chosen for something that's more user involved, but I think it gives you more control over things, especially because you might have some non-trivial stencils that we would like to do this with, right? Your stencil might be slightly lopsided or something like that, right? So in order for that to work, what you're going to have to do is, so C40, 100, 010, and 001 are your standard finite difference stencils, right? These are just functions that I have created. They are your fourth order finite difference stencils. The first step, you fill the structure called local first derivatives, right? And for the next step, you need the coordinate transformation Jacobians. This is provided to you by CapyrX, but it's easy to get them wrong, right? It's if you have to manually type the Jacobian components that you need for a derivative, that's kind of hard. So we have this structure here called Jacobians, and we have a macro that, given some point descriptor for your CarpetX loop, it just fills it in for you with the proper Jacobians in the proper order. And finally, we have this function here called project first. If you're doing a second derivative, you have project second. You pass your local first derivative, doesn't matter if they are lopsided or centered or whatever, and you pass your Jacobian data structures, and boom, you're done, right? So this variable now contains your global x, y, and z derivatives ready to be used for your wave. And this is just how you do it, right? So this is just an excerpt of the WaveToy example, right? So here I am just refilling the variables with the dx, dy, and dz derivatives. And you can do something similar for second order derivatives as well. This is basically all that I did to modify CanudaX in order for it to be able to understand these, these projections, right? And this structure is especially useful there because, for instance, for the shift evolution, it uses a lopsided stencil. For advective terms in the shift, it uses a lopsided stencil, and so this just makes it easy to work in those cases, right? And so this WaveToy thorn, it comes with CapyrX. When you check it out, when you download it, you get access to it, right? And here I have an example parameter file. I decided to do something interesting here, and I didn't really need to do this, but I just wanted to show that this works. So I've called in box and box, just to see that we can get some mesh refinement levels in the central Cartesian patch, right? And the rest of this is just, standard parameter file lingo. Oh, this is really important. The blocking factor, this is a very specific CarpetXism. CarpetX likes to divide grids by something it calls the blocking factor. And if you don't set this to 1 for multi-patch, you're going to have a hard time getting things to work. So this is basically just required, right? And here, of course, we set, our inner boundary radius, our outer boundary radius, the number of cells we want to use. Here we place our boxes. Now this is, if you have used box in box before with CarpetX, things are a little different. You have to think in terms of the local coordinates of the Cartesian patch, right? And so these box radii here, they are not really the actual radius of the box, but because local coordinates all extend from -1 to 1, this is basically a percentage of the size of the box you want, right? So this is saying that I want a refinement level which is 80% the central patch, and then I want another one which is 60%, and then I know another one which is 40%. And I'm just setting, some linear extrapolation boundary conditions shouldn't really matter that much here, right? And then if you want to run through this, this is going to take a little while. This is where you submit the job, and then you have to do some waiting. You can have some tea while you wait, right? But the final result is you're going to have something that looks like this. So this is a non-spherically symmetric quadrupolar wave evolving in our multi-patch grid. Now, this is a visit-produced plot, right? Because that's the most convenient visualization tool we have right now. And this is a real zoom into the central region, right? But you can see that the coordinates are, slowly shifting from flat to something that is spherical as we move out of the grid, right? And then we have these multiple levels of mesh refinement here working. Right, so we are closer than we were before to getting a production binary black hole run. We have many of the ingredients. Some of the ingredients are missing, but we are working towards getting them. And I think I've spoken for like 45 minutes or so. So this is basically all that I want to show you guys. And if you have any comments or questions and concerns, I guess this is the time. So thank you.
Thank you so much, Lucas. Do we have any questions? Right here.
Yeah. Very impressive work with this. I'm very curious
Hmm?
what the error looks like with plotting the same. You see any evidence of reflections, an oddity, in fact, you saw something that's running around on a proxy grid on the inside.
Right. So I do see reflections, but I didn't. Oh, yeah. Sorry. Yeah. Repeating the question. So Zach asked if how does the error look like when you have these wave fronts just changing grids and changing from flat to spherical? I do see errors. Haven't done a consistent numerical analysis of the amplitude of the errors we're getting with these transitions. Eric Schnitter, which is our my main collaborator in this work, he has suggested that we do a scaled error test, right, to see how much reflections we get in proportion to the wave amplitudes and as we go to far radii. But we haven't done that yet. But we do get reflections, and I think that's inevitable. But when we eventually get, characteristic interchange between the patches, maybe we can get that working better. We'll see. But we're not there right now. It's just we're just doing interpolation in between the boundaries to communicate stuff. So we're gonna get some reflections.
Sorry, a bit closer. So Roland has his hand up. You go first, and then Levi, you go after. Okay. So first, Roland.
Okay. Hi there. Thanks for the talk. I have a question concerning mesh refinement in the curvilinear regions, and also having non-uniform mesh refinement. So really have only, say, refinement in the angular direction, not in the radial one. Is this planned? Do you have an idea how hard that would be?
So let me see if I understand the question. If we can have mesh refinement in the angular region, so let me clarify something. I have not tried doing mesh refinement in the CarpetX sense of mesh refinement in the non-Cartesian patches yet, right? The only sort of mesh refinement I did was, box and box like mesh refinement in the central Cartesian patch. So I haven't tried to do adaptive or otherwise mesh refinement in the non-Cartesian patches. But you can control the radial and angular resolution via parameters, as you would expect, I guess. Does that answer your question?
Yes, unfortunately in the negative, but yes, it does answer the question. Thanks.
Yourself? Live?
Oh, hi.
Yeah.
Do you have a Python script which can read the OpenPMD data, which contain the multiple level of refinement?
A what grid, sorry?
Do you have a Python script which can read OpenPMD format of the output,
Oh,
which contain multiple level?
yes. Yes. So CapyrX, I can try to show you this with my VS Code. Maybe that will not fail me miserably. Let's see. But CapyrX, when you check it out, wow, my computer is really a 90s computer. You click it once and then it opens 5,000 windows. Great. So when you check CapyrX out, I'm going to try to show you guys the repository structure here. But you do get a folder with some scripts, right? And in one of those scripts, you're going to find a Python script that reads CarpetX multi-patch data and creates a plot out of it. Well, I don't think this is going to work. But anyway, yes, there is such a script, and it is in the official repository. Now, I kind of ditched that approach because that script was horribly slow, being Python, right? But it's still usable, and it still produces plots. Using Visit, it's much more convenient and much easier. So I guess if we're able to, just optimize our output, Visit is probably the thing we want to have.
I see. But have you tried the box-in-box case for the Python script?
No, I don't think I have, because the Python scripts that I have don't give you the ability to plot the grid. So, so what's going to happen is it's probably going to produce a plot, but since you can't visualize the grid anyways with those scripts, you're probably not getting a picture that looks as cool as this, meaning you don't get, the mesh with that. That's one of the things that Visit makes it easier. You can just tell it to draw the mesh and it draws the mesh. It's pretty convenient.
Okay, thank you.
Any more questions? Peter.
So going back to your time integrators, so
Right.
you get an improvement in speed, but you also pay a price in memory usage, right?
Yes.
How much is that?
Right. So the price. So the runs that we showed you guys were all GPU runs, right? So, oh yeah, sorry. There was a question about. Yeah, thank you. I guess VS Code. So there was a question about our hybrid time integrators. They have a trade-off between speed and memory, right? Because we have to store extra information about past time levels. We are paying a cost in memory for that. That does not come for free. And Peter's question was, if we have an idea on how much that cost is, right? And so so the cost that you're paying is you're storing one extra grid function in cactus terms, right? You're storing one extra grid function per right-hand side on your state, right? So for instance, say that you have 10 variables that you want to evolve in your state. You have to store 10 extra right-hand sides, right? So you pay a cost proportional to that. Now, we did not notice any penalties in the terms of speed up, meaning it did not prevent us to get that extra memory requirement did not seem to prevent us from getting extra speed ups, right? So even though we are paying a cost, as far as you can tell, it seems to be an acceptable cost in the sense that we didn't tank performance by doing that. But of course, I guess you should be aware of that, right? If you use these methods, your memory requirements are going to increase. And depending on multiple things like resolutions that you want, that may or may not be acceptable for your case.
Any other questions? Here, anyone?
All right.
Anyone else online? Do you have any more questions? No, so I'm not seeing anything.
All right.
So let's thank Lucas again.
Thank you.
Thank you, Lucas. Okay, so we are coming back at 10:30, right? We have a coffee break now. And for those of you online, we will be back just 5 minutes before that. And yes, probably stops the recording. Oh, I will leave this.